Hello everyone and welcome back. So in the last lecture, we discussed about the fundamentals of blurring from a ray tracing point of view or the geometric optics point of view. So we have found about something that is a blur circle, and we have seen that a point source is spread over that blur circle, which is representative of blurring in any imaging system. And we ended that lecture with something that is known as a point spread function. So in this lecture, we will be discussing that in much detail. If we revisit blur circles, we have seen that if we offset a point away from the object plane by delta z, we have seen that the imaging plane is also shifted away from the sensor plane. This leads to formation of a blur circle over the sensor plane where this point information now is spread over a circle. So this point information forms an image here, but this is now spread over a circle when captured over the sensor plane. If represented in this form, this is just spreading of information it's like a map from a point to an area. So we need a function that maps this, and this is something that is known as a point spread function. So this is nothing as the name suggests. This suggests the spatial distribution of intensity within this circle corresponding to a point information. So if we define point spread function in a more systematic way, it is something that describes how a single point of light is spread out in an image, or how a camera responds to a point source on an impulse. So an impulse, in a functional form, it looks like a Dirac function kind of thing. And when it passes through our optical system, it leads to a signal which is spread over an area. So this point to spread is defined by the point spread function. Mathematically, it can be represented as an intensity a spatial distribution of intensity in the image plane. So that is something in a way we can define the point spread function. And it is a very powerful tool if we want to describe image blurring. So image blurring can be, or the blurred images can be modeled as convolution of the original image with point spread function. What do we mean by convolution? That we will discuss soon. And this convolution actually is a very generic term. It is a mathematical operation and can be used in a variety of ways. And sometimes we call this function that is used to convolute other function as a kernel. So that's how this this point spread function is sometimes also known as a blur kernel. And here is a schematic representing that. So this is the object actually, and this is the point spread function, and we can convolute this object with this point spread function, and you can see this leads to formation of a blurred image. So here the image was roughly in focus, and if you artificially convolute it using this point spread function, it leads to an image which looks very similar to a blurred image. So let us now discuss about a few standard point spread functions which are very popular in literature or in practical implementations. So the simplest one is the box point spread function. Here it is assumed that the intensity is uniformly distributed within a circular region, and this circular region corresponds to the blur circle. This is represented schematically here, where you can see that the intensity is uniformly distributed within in a functional form. It looks like this. So you have this in the Cartesian coordinates. This function h represents your PSF, and you can see here the value 1 is just normalized by the area of the circle, right? That's how if you integrate this over the area, you will get 1. And if you are outside this circle, it's 0. So this represents you are being inside the circle, and otherwise it's 0. In the polar coordinates, it looks much simpler. If your radius of the radial position is within the circle, you will have this 1 by c square by 4, which is nothing but 1 divided by the area of the blur circle. The problem with this PSF is it's although it's a very simple model which can be used to defocus like to model this defocus blur, but it is ineffective for to be treated as a general blurring model for any imaging system. Also, this PSF has a sharp boundary, so there is a discontinuity at the end of this PSF, which is also we not typically see in any of the imaging systems, but it is still very useful, and it is sometimes used in superposition with some other blurring models to emulate a scenario. So the next one is Gaussian point spread function. As the name suggests, in this we assume a Gaussian distribution of the intensity. As you must know that Gaussian these Gaussian distributions are not bound. Their tail asymptotically approaches zero. So basically, it means that they approach zero at infinity. So you have to define a parameter which tells you about the extent of this spread, and the standard deviation of the blur kernel or PSF is one such parameter which appears in this equation. You can see if in this equation this r square is appears with sigma square. So basically sigma is something which is bounding the kernel in the radial direction, and we treat it as a representative length scale for this blur kernel. So this blur kernel is smooth. It has been observed that this blur kernel appears frequently in a lot of imaging systems, and hence can be used as a generalized model for a particular kind of imaging system, if I put it in a more explicit way. And these non-sharp boundaries are because of effects like diffraction or aberrations in your imaging system and other effects. So this earlier model of box function is an idealized one, where you assume that the blur circle is uniformly illuminated, but here you see that there is no defined boundary for the blur circle, and that creates a problem in a way because we are assuming a model here which doesn't have any boundary, and in the previous ray optics ideologies we have seen that there exists a boundary because there is a cone of light and things like that. So here to bridge those two ideas, we scale the problem in a way that this standard deviation is proportional to the blur circle radius basically, and there appears a constant which we treat this as an experimental constant for the system. So this is a very effective model which we will use a lot in all of our analysis, and we will also discuss in which kind of systems this PSF exists because it is still an approximation. Coming to airy disk PSF now, it still has a Gaussian like distribution in the center, but then you will see rings around that center or waves. So if you look at this schematic, you can see here that there is this dome which looks like a Gaussian dome, but then you have ripples around it or rings around it. Those are actually an artifact of diffraction. So this is something which is a more exact PSF based on wave optics. Gaussian is just an approximation for the central dome of this, and we assume that these ripples around or the rings around are weak. So that's why Gaussian PSF, although it is very efficient, it's still an approximation. Here you can see the functional form of airy disk PSF looks very complicated. That's why using this directly in systems sometimes can be very tricky. But yeah, this will be more accurate for sure. This PSF also has a very sharp, like very smooth boundary, and it asymptotically approaches zero at the end. But you will also see some nodes where this value is zero because it's an interference pattern. So you will see a fringe kind of pattern. Where you will see nodes and antinodes. The speciality of this is that this will exist even when your system is in focus. So this is a limiting condition for any system. So this is the amount of blur that will be there always in your system. But if you also introduce defocus, then you have to account for both the blurring induced because of defocus and also because of this interference, that is iridescence. So then you have to have some superimposition model for that, and sometimes modeling this wave optics based or diffraction based PSF for such defocus system very challenging. So typically we will stick to Gaussian PSF in all our analysis for the simpler implementation and design of systems. But yeah, if you are working with say coherent light sources and maybe lasers and things like that, you cannot avoid these airy disks and fringe patterns or interferences. Just to compare, here we are comparing a Gaussian PSF with an airy disk PSF, and you can see the central dome can be approximated pretty well using a Gaussian PSF. So that is actually the idea of a Gaussian PSF. So it is not something that is appearing from the fundamental equations of optics, but it is an approximation for the central dome for your airy disk PSF, which is something which you can estimate using wave optics or uh, the interference pattern that is generated considering the light rays originating at the edge of the light cone from the aperture, something like that. So you can refer to the any of the optics book and you can clearly find how this airy disk is formed. But yeah, we will stick to Gaussian PSF. Now we have a model or a functional form of the spread of intensity within a blur circle. How to use that information? Uh, we can use that information to emulate blurring. Say if you have an original image and you want to artificially blur it, you can impose these point spread functions to generate those blurred images. And convolution operation is something that is extremely useful to do that. In a functional form, it would look something like this. So you have a original image, you convolute it using a point spread function, and you will generate a blurred image. In the discrete form, it will look like this. Why in discrete form? I will discuss this. But you can also represent this in a continuous form where the summation signs will be replaced by your integrals. So this schematic will be very helpful to explain the convolution. Say you have an array of numbers. So this is nothing but kind of a matrix, and you have this convolution operator here, which is also a matrix. So what you do is you treat this convolution as a moving window. So you place this window aligned with this cell highlighted here, and perform the operation such that each of these elements are multiplied with the element of the source. So this source image elements are multiplied with the weights. So you can treat these values as weights and then take the sum. So it is kind of a weighted summation or weighted average kind of scenario. So what you will do is you will do that. So this is just element wise operation that is represented here for this 9 elements that are available, and you will assign the final value to this updated image or updated matrix. So yeah, it can be slightly difficult to move your brain around this idea, but yeah, just give it some time and maybe you can try this out on a piece of paper and you will understand this more easily. So you do this again and again basically. Now you shift the window to the next cell, do this again. Again the next cell, do it again. So what you just do is whatever is occurring within the window, you apply the weights associated from the convolution operator, and just take the sum of everything and place it in the final new matrix. Do this again with the next cell, next cell, next cell, do it again and again for all the cells, and you will have the convoluted image. So just imagine if all these values were 0 and the central value was 1, then this operation will generate the same thing again. Okay. And whatever I said is represented in a functional form here. So you can break this function down for a simple, say you take a 4 by 4, say 4 by say 5 by 5 matrix and a 3 by 3 convolution operator. You can write element by element whatever is happening, and you can match if this discretized form is correct or not. So this will be a good homework exercise, I guess, to understand this convolution operator. The same thing can be written in the form of integrals if you want to estimate it in a continuous field. Okay, some of the examples which we are trying to explain here is you can emulate Gaussian blur using a Gaussian BSF, and this is something which we are interested in because it kind of simulates defocus blurring. You can also generate motion blurring that we have discussed in the previous lecture using a PSF which is elongated in a direction of motion. So that PSF is not symmetric. All the PSF that we discussed till now were all symmetric in the azimuthal direction, right? But there can be PSFs which are like not symmetric in the azimuthal direction. Those leads to motion blurring kind of final output. Again, coming back to the fact that why discrete, because the images are something which are discrete in nature. It's not a continuous field. This is just the representation of that. Say you have an object which is mostly continuous in nature, but when they align with the sensor array, which has discrete sensors arranged in a grid, so each sensor element will collect the intensity and assign it in a discrete fashion. So your object will look something like this. So most of the time we capture it in a very high resolution, which basically means that the sensor sizes are very small. So the object looks smooth, but actually it's discrete if you look at the quantized final elements. So this is something that is known as spatial resolution. Also, even the intensity that is captured at each sensor level is not continuous. It can be captured at some finite number of bits. So this is something known as grayscale resolution. So this is not something which is really important at this stage, so I will not be discussing this. But yeah, this is something which is important for you to understand, that the information that you are capturing through any of the cameras is usually discrete. That's why this convolution operator also we are talking in terms of a discrete operator. And here is just the representative of the same thing that we discussed earlier. So you have this image, you have this moving window marked here, and you have these weights. So basically this is kind of an averaging operator, right? You can clearly see that here the weights for each of the cell is 1 by 9. So it is nothing but sum of all the elements within the window divided by 9, nothing else. So this is kind of an averaging kind of filter. And here, as you can see, that all the elements have the same intensity kind of thing. This H has all the same values uniformly distributed. So this is a box kernel or box PSF that we had discussed earlier, right? And this convolution operator will then be applied to each subsequent cells point by point till the whole space is filled, and then you will generate a blurred image for the same image. Here are some examples of some operators which can be convolved over an image to generate certain characteristics. So as I have explained, that if you take just one at the center and rest of them as 0, it will just recreate the original image, right? Because you are assigning weight only to that cell, which is again placed back in the new matrix at the same location. So it's like just copying the original image and pasting it into a new matrix. You can have the weights in a way that the center has the highest values, and as you move away from the center of this matrix or the blur kernel, the value decreases, and it can be done in a very particular way. So this is, in this case, it is done in a way that it matches with the Gaussian blur kernel that we discussed earlier. So in the same functional form, you can extrapolate that and get these values. and then you can see that it looks slightly blurred. Like, so this is the original image, here it looks blurred. This is an operator which sharpens the image. So these are some weights assigned to it, and you can see it leads to the sharpening of the image. You can also detect edges. So these weights here, when convolved over the original image, you can see that the sharp edges are clearly highlighted with a more whiter values, and darker spaces represent smooth parts of the image. So yeah, this convolution operation using a certain kind of kernels is designed for some particular application, is a very powerful tool in image processing and is extensively used. So this is an example of simulating a blur using convolution operation. Here a Gaussian blur kernel was used to blur this image, and you can see it looks pretty much blurred. Uh, and this smoothing out is controlled by the strength of the Gaussian blur kernel, which is dependent on sigma. So higher the sigma, higher is your extent of blurring. This is an example with the box kernel. Here the intensity is uniformly distributed within the blur kernel. So this is also again kind of a moving average kind of a kernel, and you can see it leads to blurring in this fashion. You can increase the strength of this kernel by changing the size of the blur kernel. Here the moving average is taken for only 9 neighborhood points, but you can take maybe 4 by 4, like 16 neighborhood points, or 5 by 5, that is 25 neighborhood points for a stronger blur. So here the extent of blurring is controlled by the size of the blur kernel. As we have discussed earlier as well, that if your blur circle size is larger, your extent of blurring will be larger. So it's the same analogy. So if you take these arrays of 1 in a 5 by 5 grid, and you normalize it by taking 1 by 25, so that the net intensity is 1, then it will lead to much larger blurring. Now that we have covered the fundamentals of blurring from a perspective of geometric optics, where we have seen the formation of a blur circle, and we have also seen what is the role of point spread function in defining the redistribution of the point source information or the light information within the blur circle. We will now try to implement it in the particular context of dispersion size measurement. So we have seen that if we have a focused image information in the form of say a digital matrix which represents the pixels in an image, we can apply a convolution operator to artificially emulate the blurring effect. In the same way, we can do that in the continuous fashion as well. From the practical point of view, we do it in a discrete way. Here it's just in this slide we are representing that in a continuous way. So we have this particle of size d naught, and we are seeing how we can this is the focused particle image, and how we can convolute it using a Gaussian blur kernel to generate a blurred particle image. So these are just the mathematical form of all those things, and when we finally substitute everything, we get this integral equation, which is crucial in certain methods where or certain forms of DFD technique. By DFD, I mean depth from defocus. So as we have seen while defining the Gaussian blur kernel, that we can approximate the standard deviation of the blur kernel with the blur circle radius. So we have put a proportionality sign here correlating both, and we can then have an experimental constant capital A, which will be dependent on a lot of factors, and some of them might not be deducible from theory. What it does is we already have a relation of this blur circle diameter with respect to the offset of the particle from the object plane, or movement of the particle in the depth direction. So this now becomes a foundational equation now, correlating depth, which is delta z, with defocus, that is sigma, because sigma is representative of the amount of blurring or defocus, and delta z represents the position. So in this form, with all the discussions that we have already had, we brought everything down to our motivation depth from defocus, where we are trying to determine the geometric parameters associated with the particle by estimating defocus in an image. So that's what our motivation is. In the next lecture, I'll be discussing in detail about this particular convolution integral equation. Here I'm just browsing over it, but there I will depict two steps of how we got this equation and how it is useful. We will define certain elements like thresholding, Fourier transforms, and other things, the tools which are used along with this idea to implement the depth from defocus to estimate particle sizes. Thank you.